Hey everyone, welcome to 5.5 bases other than e. And the question is, what if we want to differentiate like a to the x, not like e to the x or something like that? What if we want to differentiate a to the x? And I can tell you there are some ways around it. Let's start off by just doing the definition of exponential functions to base a. So it says if a is a positive real number and we're not equaling 1, and I'll show you why it doesn't equal 1 in a little bit, and x is any real number, then the exponential function to base a is denoted by ax, a to the x, and it is defined by a to the x equals e to the natural log of a x. Okay, so first question, why does a not equal 1? Well, if we have that, then we're going to rewrite this as 1 to the x, and 1 to any power, 1 to the first, 1 to the second, 1 to the 10th, 1 to the 100th is always going to equal 1. So it makes it really a trivial case. It's just a line that's really boring and doesn't help, and who cares, right? But we do have to define it saying it does not equal 1. Okay, so if we have this, and then we want to be able to take, say, the derivative of it, then we can say, now let's just e natural log of a x. So then we can rewrite this as take the derivative just like you would with any e function. All right, and the natural log of a, this is just going to be a constant. That's just some number. And now, this. Hey everyone, here's a quick reminder of all of the formulas for exponentials when x is in the exponent. So, derivative of a to the x is natural log of a to the x. Derivative of a to the u is the natural log of a to the u times u prime. Derivative of log base a of x is 1 over the natural log of a times x. And last one is log base a of u is natural log of a times u prime. So let's just do a couple. Oh, also, here's the integral of a to the x dx is 1 over the natural log of a times a to the x plus c. Okay, so real quick, let's do this one. Y equals 2 to the x. Okay, well that looks a lot like that other one we have. So if I say find the derivative, I'm really saying find the derivative of that. So that's going to be the natural log of 2 times 2 to the x. There you go. And evaluate this. That's just going to be 1 over the natural log of 2 times 2 to the x plus c. There you go. Okay, so here's an example where we can maybe do some of this stuff. The half-life of carbon-14 is about 5,730 years. If 1 gram of carbon-14 is present in a sample, how much will be present in 10,000 years? All right, so first of all, when we talk about half-life, we're saying how long does it take for half of that stuff to be gone? So really what it says is that we start with 1, we end with a half, right? And we say that is going to happen in 5,730 years. Okay, so really what we're saying is half-life, what does it mean? So what you can say is that, let's just set up an equation. Y would be how much is left. How much do we start with? 1. What are we doing to that one? We're trying to figure out how long does it take for half of it to be there, right? Okay, and then how many times is that going to happen per 5,730 years, right? So we want to know how many times are we going to take half of it. Okay, where n equals number of years, right? Because so if we have 5,730 years, we're going to say 5,730 over 5,730, and that's going to be 1. So we're going to take half of it, which makes sense because we want to have half of this 1 gram left. Okay, so how many years are we actually talking about? 10,000. So we can say y equals, do I really need that 1 there? No, but that does kind of tell you it's the principal. It's the first amount. That's the starting value. It's kind of like your y-intercept. If you think back to lines, right? So I'm just going to do 1/2 times 10 to the 10,000 over 5,730. All right, and then why don't we just grab our calculators and figure this all out? So there's the calculator. Hello. And we have 1 divided by 2, close my parentheses, open my parentheses, to the parentheses 10, 1, 2, 3 divided by 5. Woo! Thanks for saying excuse me. Or bless you. Appreciate it. It's real nice. Okay, and I do that, and we get that number, 0.298. So we can say y equals 0.29829. And what does that number mean? What are our units that we're talking about? Well, years and grams. So yes, you are right if you thought it was grams. There you go. So there's one way of just looking at this. Why do we even need to do E? Why do we need to worry about exponential functions in the first place? This is kind of just an Algebra 2 type example, just to kind of remind you of what we're doing. Okay. Here is another one. Definition of log function to base A. So the last one we did was exponential function. Now we're doing log function. If A is a positive real number, again, A does not equal 1. You know why A doesn't equal 1, otherwise what the heck is the point, right? And X is any positive real number, then the logarithmic function to base A is denoted by log base A of X and is defined as log base A of X equals 1 over the natural log of A times the natural log of X. So if we want to take the integrals or derivatives of this, could we do that? 1 over natural log of A is just going to be a number, just like A is a number. All right, it's a positive number, so you can take 1 over that. This is just some constant number. It'd be like a 5 or 3. So we'd have like 3 natural log of X. Could you do something with that? Sure. So if it's not a 3, can you still do this? Of course you can. Okay, one thing I want to mention over here, page 348 and 349, there are some extra properties that you might want to review about logs and exponents. They're really important. Just to remind you of it. I'm not going to write them all down because you should know them already. So here is the next one, properties of inverse functions. And this is just review. I want to be able to go through this pretty quickly for you. So let n be any real number and let u be a differentiable function of x. The derivative of x to the n is going to be n to the x, n times x to the n minus 1. Now, how is that different than anything we've done? Now we're saying n is a real number. And we've kind of done that before with fractions. But we could say, like, what's the derivative of x to the 1.275? Well, that's going to be 1.275 x to the 0.275, right, because we're subtracting 1. Or we could take, like, the square root of 2, or we can do any real number. It doesn't have to be whole numbers, it doesn't have to be fractions, it doesn't have to be positives or negatives. It can be anything that you want. All right, and the same deal with this one. d dx of u to the n is n times u to the n minus 1 times the derivative of u. All right, so here's a couple examples. The derivative of x to the e is going to be e x to the e minus 1. There you go. And what about derivative of e to the e? Well, e is a number to another number. It's going to be a constant. So what's the derivative of constant? It is 0. There you go. That is correct. All right. Very good. So, we're all done. Yay! And that means I know what you're saying. But Mr. Barman! Wait, hold on. I'll actually show you a video of what I'll flip the camera around so you can see what you guys look like. I took a video of you today in class and just want to show you what you look like. So that was you. There you go. Stay tuned for the next video, and I will even preview it right here. It's all about compound continuous interest, and I'm even going to show you, I'm even going to prove to you how we can go from compounding interest to compound interest. I'm going to give you a proof. Have fun.